In the last mechanism, you saw that hydroxy group was a leaving group. So if you can just take a look back here, you saw how it was a leaving group. And this is okay for a very simple reason. It's because the molecule is willing to kick out OH in order to form a conjugated product. So this is conjugated. This is sp2, sp2, and sp2. Remember, when we have a double bond, we have sp2 hybridized, which means we have empty p orbitals, and then they interact with each other, which forms conjugation. So this is why OH is okay to leave. Now, there are a few things we need to talk about with the aldol condensation. So number one is aldol reaction. An aldol reaction is an equilibrium process, and the concentration of the aldol product at equilibrium depends on the substrate used. So notice I used equilibrium arrows. So this is an equilibrium process. And if you recall from Gen Chem 2 that the concentration plays a role in forming the product. So, but we also need to know what substrate we're using. So you're going to see that if we have an aldehyde, just like this one, which is basically the last reaction. And let's just redraw the product here. I'm only going to draw the aldol addition product. Because we need to discuss this in this context. So that's basically this right here. At equilibrium, this is 55%. So this is favored at the equilibrium. Now, the moment you have a ketone, when you have two ketones reacting with each other, the reactants are favored, so the reaction is less likely to take place. So the product of this, I'm going to redraw another one. And this is something that you need to, again, just practice, practice, practice. So let's say this was, delete this here. Let's say this was our alpha carbon for the enolate. And let's say this was the carbonyl, the electrophile. So the product would be CH3 . Okay, so notice the highlighting. So what's different about this is, you have two methyl groups. That's a ketone. Here you had a methyl and a hydrogen. So this reacting with each other. So here's the difference. Okay, so this is only 1% at equilibrium, meaning the reaction is not favored. And for a simple reason is you have sterically hindered. Remember, ketones are more sterically hindered. So that dropped it down to 1% at equilibrium. It's huge, very huge. So the equilibrium must be driven to get the reaction to go to completion. Both reactions can be forced to completion by dehydration, and that's the exothermic dehydration drives the aldol equilibrium to the right. So if you notice here, here's how we can do it. So we have 2 moles of this, just like that. You have to have the same conditions, but notice what I'm doing here is I'm adding heat. So we need exothermic dehydration. Then you're able, believe it or not, with heat, to form 100% conversion. So once again, you need heat. That was the key ingredient here. And you're able to actually produce the dehydrated product at 100%, at least close to 100% rate. Now, there's a problem when we have 2 different carbonyls reacting with each other. So it says here, when the enolate of one aldehyde or ketone adds to the carbonyl group of a different aldehyde or ketone, a mixed or crossed aldol product is obtained. The compounds to be used in a crossed aldol reaction must be selected very carefully, or a mixture of products will be formed. Okay, that's why it's called crossed or mixed. Either one is fine. But I hope you understand what this means. So this is what it means. It means if you have a flask, round bottom flask in the lab, and you put acid aldehyde right here with another aldehyde in this case. So you have, notice there's 2 different groups. So that's, let me actually go back to this. Okay, so you have 2 different aldehydes. The question is, you look what happens here is how many products you get. You actually get 4 different products. 4 different products. So you might be thinking, how do you get 4 different products? You get 4 different products, and this is really something you need to think about, because you can form an enolate, let's say on this one, and it reacts with itself. An enolate, and it reacts with this one, with the other starting material. Now, and you repeat, you do the same thing here. This one can react with itself, and this one forms an enolate and reacts with the other starting material. So let me show you what I mean. Okay, so we need to label them. Okay, we'll call the first one A, and we'll call the second one B. We have to distinguish between them. Okay, so how does this form? This forms when you take the enolate of A and add to A. So this one is reacting with itself. The second one is when you take the enolate of A and it adds to B. Okay. There's no space here to show you all of that, but I will show you one or two. And then this one is the enolate of B, and it adds to A. And then this one is the enolate of B adds to B. Okay, so let's show you. We did this one before. So let's show you the enolate of A adding to the enolate, adding to B. So let's look at that. Okay, so here's yellow. Here's green. Okay, let's do that as well here. Here's green. And here's yellow. This is CHO, means it's an aldehyde, the whole thing. And you can actually repeat the other one. Now, the whole thing about this is that this is not a useful reaction. Not a useful reaction. Not useful at all because you get a mixture of products and they're hard to separate. Generally, that's a bad option in organic to get a mixture of products. You need pure products. So we will see in the next video ways around this.